If I would tell you that length, area and volume are the same, you would probably think that I'm crazy. So I will not tell it to you, but I will tell you that length, area and volume and their generalizations could be generated from the same mathematical abstraction which exists in linear algebra. And this is the topic of the present lecture. Length and distance are terms that we are intuitively understand and use from a very early age. Now I want to shock you even more and to say that most probably you have no idea what length or distance is. You are probably thinking, wait a minute, this is silly, I know what I know. Length and distance is something that I can measure with a ruler, or measuring wheel, or maybe some other devices like GPS or laser, or something more advanced than that. I know even how to find Euclidean distance between two arbitrary points. While all of that might be true, I still claim that your conceptual understanding of distance could be lacking, or even wrong. Simplicity of distance is an illusion. It is more complicated than you think. I will demonstrate that with examples. In this example problem, we have a rectangular park like that. We need to get from point 1, which will be here, to point 2, which will be here. We want to find the shortest way we could find between the point 1 and point 2. And the question is if we should go straight by the trajectory A, or we should go around using B and then C. In other words, we are asking a simple mathematical question. Is A larger than B plus C? Is that the same? Or A is basically shorter than distance B plus C? The mathematically inclined among us immediately spot the shortest trajectory between 2 points, and this is of course trajectory A, because it's a straight line between point 1 and point 2. So A should be shorter than B plus C. If you disagree, then maybe you know something that I don't know, and you need to take a course in more advanced math. Assuming that you agreed that A is smaller than B plus C, I propose to do the following. Let's divide the side B, the distance B, by half, which will be that point, and we will divide the distance C by half, which will get us that point. And then we will take that side and move it here, and we will take that side and move it there. So, since we have a rectangle here, we haven't changed any lengths so far, which means if you're going from the point 1 to B, and then you go from B to that point, and then from that point to C, and then from point C to the point 2, this is exactly the same distance as you will go first from 1 to B, then from B to A by that trajectory, and then from A to C, and then from C to 2. Why? Because this segment exactly equals to that segment, and length of that segment is exactly the same length as of that segment. Okay, we have shown so far that B1 plus B2 plus C1 plus C2 is the same thing as B plus C, because if you replicate the original triangle and you put here B2 tilde and this one is C1 tilde, because this is rectangle, C1 equals to C1 tilde and B2 equals to B2 tilde. So those two together are basically our previous C, and those two together our previous B. So our B equals to B1 plus C1 tilde, which is C1, and C equals to C2 plus B2 tilde, which is B2, because those two are the same and those two are the same. So the overall distance is exactly the same. So the red line and the blue line distances, total distance is exactly the same. Now, we can continue dividing every single triangle by half, which means we will divide B1 distance by half, and B2 distance by half, C1 distance by half, and C2 distance by half, and goes that way. Now, instead of going all of the B1, we'll be going first to the middle, and then down, right, down, right, down, and so on, until we get to the point 2 from point 1. Now, the overall distance will be exactly the same, because all of those things are rectangular, which means that this side equals to that side, and this side distance equals to that distance, right? Okay, now we divided instead of 2 triangles into 4 triangles, but red trajectory we haven't changed the distance at all. So the entire distance that was like that, in red, with 90 degrees here, this is the same trajectory like we have right now with B11, B12, B21, and so on. Why is that true? Because compared to the previous one, which was like that, clearly B1, which was here, and B2, which was here, could be written as B11. So B1 could be written as B11 plus B21, and B2 could be written as B12 plus B22, because this is the addition of those two sides. And C1 and C2 also could be written as sum of those two segments. So taking this segment and this segment will give you C1, and taking this segment plus this segment will give you C2. And this is still the same B plus C that we had from the beginning. Again, we can continue the same operation, dividing that into 2 and getting a little bit more zigzaggy trajectory. So we get more stairs, and we're getting actually closer and closer to A. But pay attention that the distance, which was B plus C, is not changed in the red line. So red line is still the same total distance of B plus C. Let's take more steps, and we'll getting more and more of those zigzags, closer and closer. Now, since we can do as many steps as we want, we can get as close to A as we want, which means that the length of the red line here is B plus C, and the length of the black line is A. So we can put it in any tiny corridor here we want, so we can make it as close as possible to A with any precision we want. So we can get closer and closer and closer until both lines will be indistinguishable between them. So does that mean that A equals B plus C? Because this would not make any sense, right? But maybe it is. Just stop for a second and think about that. Do you really think that we've got to some paradox? Or actually B plus C equals to A? Or A still should be much shorter than B plus C? Because this was the original distance. This is B plus C. So pause the video and think about that for a second. Okay, the correct answer is of course that A is still smaller than B plus C. But why they could be that close? This is a question. And the answer to that is that two lines which are almost indistinguishable between them, so they are as close as you want, could have completely different lengths. And this comes from our idea or understanding of what distance is. Because when we're talking about distance in a regular intuitive sense, we always assume something like piecewise linear distances between 2 points. We never think about something which is zigzaggy lines of that kind, or some line which is not smooth, and how you measure the distance on not smooth line which is jumping from one place to another. we always assume that we have some straight distances between two close enough points. So this is just approximation of the distance. But technically speaking, you could get any distance between those 2 points, which will be as close as you want to distance A. I want to give you another example of distance measure, which shows how wrong we could be about distances and our understanding of distances. For example, Wikipedia says that border between the United States and Mexico stretches 1,954 miles from the Gulf of Mexico to the Pacific Ocean, and this is shown here by that red line on the map. Now, the question is how actually they measured that. Let's say you measure some distance between 2 points. So you have point 1 and point 2. If those points are close enough, you can measure that just by straight line between those points. So your border will be classified as just straight line between 1 and 2. Now, let's say you are zooming in and trying to get a little bit more details from that border that you are measuring. And the actual border looks like that. In the closer look. So clearly this line is longer than the original line. Now, you will approximate that by straight lines here, and straight line here, and straight line here, which is just piecewise straight approximation to that borderline. Now, you want to go even in more details, a little bit closer areas. So you're measuring that with much smaller lines, which probably will look like that. So this is our new border. And if you're measuring straight segments of that border, the overall line between 1 and 2 will be much, much longer than the original blue line, and then even longer than the green line, because it gets more zigzags in that line. Now, if you get even to atomic level of measurement, you can get almost to infinity distance, which means how long is the distance of the border depends on the length of your instrument measure, which is unit of measurement. Like if you're taking, for example, that border as segment here, which all of them straight, you'll get one length, and so on. If you'll take it with more details, like it's going like that, it will be much longer distance. But if you get even more details, then this border looks like something very noisy line. This could get to any distance you want. It depends on your measurement instrument. So the meaning of distance measure should come always with the size of the measurement unit that you're using. For example, if you're using like 1 foot as measurement distance, you will get completely different border lengths than if you are using 1 mile as your unit of measurement. So it's completely different. I hope that you are surprised enough to stay open-minded about new things that I'm going to tell you about distances, areas, and volumes. If you want to learn more about distance measurement, you need to study fractal theory. But this is outside of the scope of this lecture. Now I want to talk about what is distance, how formally we can define distance function in math. Generally, this function is defined between 2 points in space, which could be 2-dimensional space, or it could be 3-dimensional space, or it could be any dimensional space, so it could get to n coordinates. So in 2-dimensional space, you'll have just x, y. In 3-dimensional space, you'll have x, y, z. In n-dimensional space, you will have more coordinates, so this vector will be just having more elements. So formally, the distance function, or metric, as it's called in math, on a set X, which could be any set of Rn or Cn, it could be vectorial space or any other space, is a function defined like that. So this function is working on z set multiplied by the same set, which might be Rn multiplied by Rn, which is vector and another vector, so you're taking two vectors and mapping those two vectors into interval from 0 to infinity, which means all positive real numbers. This is defined by the following four properties for all A, B, and C that belong to X. Now, let's see what it means first of all. It means that A could be just some scalar number, or it could be any kind of vector, so it may be something like that. A1, A2, A3 for three-dimensional space. Or it could be A1, A2, A3, A4 for four-dimensional space. The same thing happens with vector B and vector C. So all of them belong to that X set, which might be Rn. Now, any function which satisfies the following four conditions could be a metric. This means already that this is not unique function which we'll call distance. You can have million of different functions, all of them could be defined as distance function. So this is not unique function which is distance. You can define many different functions which will be distance functions. Now, what are those four properties? Here you have them. The first property is obvious, it's called non-negativity. So the distance between vectors A and B should be always larger or equal than 0. So it's always positive or 0. So distance clearly cannot be negative number. Now, the second property is uniqueness of 0, which means distance may have only one 0, only one possibility for vectors A and B to produce distance which is 0. This is true only if and only if A equals to B, which means the distance will be 0 if A equals to B, and if A equals to B, the distance will be 0. So this works in both directions, if and only if. Third property is property of symmetry. The distance between vector A and B is the same as the distance between vector B and A. So you can replace the order without changing the distance function. And this is obvious because the distance between one point and another point is the same distance as from the second point to the first point. And now the most important property that we are talking about is triangle inequality. You know about that inequality from numbers. So in numbers this inequality looks like that. Absolute value of A plus B is smaller or equal absolute value of A plus absolute value of B. In terms of distances, this rule says that the distance from point A to point B plus distance from point B to point C is always larger than distance from point A to point C, and we saw that already in our triangle example before. So if you have point 1, point 2, and point 3, the distance from that point to that point plus distance from that point to that point is always larger than this distance between those points. As I said before, any function which satisfies those two conditions could be a metric or distance function. In the case of linear algebra, we will almost always use r to the power of n, which is n-dimensional vector of real numbers, as set x. Here are a few examples of different distance functions. First of all, we are talking about Euclidean distance. This is kind of standard distance that we all know about. So Euclidean distance for vectors A and B, which both have the same dimension n, which in other words means that vector A is something like that, and vector B is something like that. They could be also transposed to make them column or row vectors. So the distance between those two vectors is defined by that formula, which is the Euclidean distance between two vectors. What is the meaning of that thing? So this thing is basically square root of each element a1 minus b1 squared plus a2 minus b2 squared plus and so on until you get to the last element an minus bn squared. This is basically Euclidean distance. In regular space, which we know which is two-dimensional space or three-dimensional space, this will be a regular distance between 2 points. So if you have point 1 here and point 2 here, this will be your point A and this will be your point B, then the distance will be that green line here, which is straight line between 2 points. And this is Euclidean distance, the length of that straight line. So this is D between A and B in Euclidean sense. Now, another kind of metric is Manhattan distance. So Manhattan distance is also called L1 metric compared to L2 matrix in Euclidean. And the number 1 and 2 coming basically from the power of the difference, because this is power 1 technically. So the distance is defined like that. This is sum of all of the differences of all of the appropriate elements in the vector, which means basically absolute value between A1 and B1 plus absolute value between A2 and B2 plus the last one, all of those values, AN minus BN. So this is just sum of absolute distances. Pay attention that you can draw it in multiple different ways in basic space. So you can draw it as distance from this line plus distance here, or you can draw it as distance here plus distance here, or you can go by any other zigzag like that, or any other zigzag you like. The idea is that you need to get from the initial point 1 to the final point B, and total distance that you will be going is exactly the Manhattan distance. Now, the reason it's called Manhattan is because in Manhattan you have that kind of streets, and another name for the same distance is taxi cab distance, which means that you just need to drive by the streets and you cannot drive by diagonal through the buildings. Since the streets are orthogonal or perpendicular to each other, all of the distances will look that way as I just drawn for Manhattan distance. Just to remind you that this is called L1 metric. You have many other distance measures which are called Minkowski metric, Riemannian metric, Hamming distance, which is very popular in coding theory, or graph metric, and others. Now I want to show you formal proof that this function is a metric or distance function, which means something which is defined by that formula satisfies all of those 4 conditions of metric. Otherwise, I cannot call that function D metric. Now, let's test the first one. The first one, the distance should be always larger than 0. So the first will tell us that D AB always larger or equal to 0. So our distance as defined equals to the following. This is A1 minus B1 plus A2 minus B2 plus and so on plus AN minus BN. Now, since we are taking absolute value of every single distance between the single elements like that, this thing is clearly larger or equal to 0. This thing will also be larger or equal to 0. And all of those components will be larger or equal to 0. They will be equal only when A1 equals to B1 here, and so on. So if you're adding all positive or at least not negative numbers, clearly you will get something not negative. This proves the first property that D is larger or equal to 0. Now, second property, that D equals to 0 if and only if A equals to B. So let's prove first that direction. So if the distance is 0, then all the vector A then equals to vector B. So what it means that D equals to 0. So D equals 0. This is what we are trying to prove. So d equals to 0, it means that a1 minus b1 plus all of the other elements, an minus bn, all of that equals to 0. Now, that expression could be 0 only if all of those things are 0, because those are non-negative parts, which means that this causes a1 to be equal to b1 and so on, an equal to bn. So all of those elements of vectors a and b have to be equal to make that thing true. And from that one we get actually an, a general vector, equals b general vector. Now, the other direction. So how we prove that? So a equals to b, this is what is given, and we want to prove that the distance will be 0. If a equals to b, this means that a1 equals b1, a2 equals b2, and so on, an equals bn. This means that also a1 minus b1 will be 0, and so on, an minus bn will be 0. Now, if those distances are equal, then also absolute value of them will be 0. And if you get that thing back to that equation, clearly it will give us distance 0. So this proves the second part. How about the third part? Third part is also easy, since our d of AB is basically sum of absolute values of a1 minus b1 and so on to an minus bn. It also equals b1 minus a1, since inside of absolute value you can change the order. So technically this is what it says. Because it doesn't matter if you are changing the order of subtraction for any numbers, and those are just scalars, right? And then you're completing that with bn minus an, and this is exactly the distance that we wanted, which is ba. So we have proven the third one. Fourth one is the most interesting one, which is triangle inequality. So let's write what we actually want to prove. We will start with that part first. The distance between A and C is essentially A1 minus C1 plus B1, sorry, this is not B1, it's A2 minus C2 plus, and so on, plus AN minus Cn. And now we will do some small trick here. We will write that in a little bit different manner. In each element we'll write A1 minus B1 and plus B1 minus C1. Now, since B1 minus B1 is 0, so it's not changing anything here, but it's a small trick here. The same thing I'm doing for the second one and for all of them. So I'm doing A2 minus B2 plus B2 minus C2 and so on until you get to the last one, and you get AN minus BN plus BN minus Cn. Now, since this is addition and subtraction inside of the absolute value, we can just put those two together and those two together without changing anything. And we put in the same way those two together and those two together, we combine them, into parentheses. Now we want to use a regular triangle inequality, which you learned in school. So regular triangle inequality says that x plus y is smaller or equal for numbers x and y, not vectors, smaller than x absolute value plus y absolute value. This is triangle inequality for numbers. For example, 5 plus minus 3 is smaller or equal 5 absolute value plus minus 3 absolute value. Which is obvious because if those two numbers are positive, then it's always equal. But if one of those numbers is negative, then the absolute value of that number will be larger than that number itself. Now, pay attention to what I'm trying to do here. I'm trying to divide that into two parts, that part and that part. So this will be my x number and this will be my y number in that inequality. Now, pay attention that a1 and b1 are scalars, so this is actual number, and b1 and c1 are also numbers, so y is a number. So I can write for each one of those, I can write something like that. So it's smaller or equal absolute value of a1 minus b1 plus the second absolute value of y, which is b1 minus c1. So that's it with that part. Plus, now we move into the second one. Absolute value of a2 minus b2 plus absolute value of b2 minus c2. And so on until we get to the last one, and then we write an minus bn plus bn minus cn. But pay attention, what is that? This is exactly the definition of DAB plus D between B and C. So this is exactly what we wanted to prove. Here we will talk about something very related to distance, but a little bit different. Length generally is not a distance between 2 points of vectors, but it's related to size of something. So distance and length are very related, but used in different situations. Distance assumes some reference point. Like it makes no sense to ask what is the distance of the table, unless you state that you are looking for distance from one corner here, for example, to another corner here. Then it's distance between those 2 points. But you are saying that this is length of that table. In other words, length is a distance that is measured from the origin or some other reference point. The generalization of term length or size in math is a norm. It could be generalized to vectors, matrices, or even functions. Norm is one of the most popular terms in linear algebra and functional analysis. In scientific literature, it's used everywhere. It is so popular that some people prefer to use it instead of distance, length, or size, and often misuse it. So what is norm of a vector? A norm is a function again, which we denote by double bars or double vertical lines from two sides, and here will be the vector inside of that, so norm of something will be a function from Rn, or it could be also complex numbers, but we will be talking about real numbers only. So this is from vector, so you're taking some vector x, or a or b or whatever vector is, and map it into real numbers. Now, those real numbers also will be positive or zero. And it should satisfy the following conditions. The first condition, second condition, third condition, and fourth condition. Now, this will happen for all a and b that belong to our Rn. So technically speaking, a will be equal to something like that, and b will be vector b1, b2, and so on to bn. And this should be true for all alpha, scalar alpha, in real numbers. So alpha could be any real number you want. So let's see what properties we have. Norm of vector A is always larger than 0. And it's natural because we are talking about length. So length is clearly larger than 0, which is basically distance from 0 to the point A. Now, second property is also very similar to what we saw in distances. So the size of vector A, or norm of vector A, is 0 only if the vector itself is 0. Another property of norms is if you multiply some vector by some scalar, and I remind you that multiplication by scalar means that every element of the vector will be multiplied by alpha, like that, then you can take alpha out of the norm with absolute value. So it's multiplication of absolute value of alpha by the norm of A. And finally we have triangle inequality as we had with distances. So the size of A plus size of B is always larger or equal to size of A plus B. If norm is defined, the metric could be also written like that. So distance between A and B is just norm between A minus B. Now I can show you a few examples of norms. Let's say you have some vector A, or it could be also transposed version of that vector. So Euclidean norm, which is written as norm 2, is square root of sum of all of the squares of elements of vector A. In other words, it's just square root of A1 squared plus A2 squared plus and so on until you get to AN squared. Manhattan norm, which is of course related to Manhattan distance function, is norm 1 and is defined as sum of absolute values of all of the elements of the vector A, which is A1 absolute value plus A2 absolute value until you get to the last one, AN absolute value. There are other norms like maximum norm. It's called norm infinity norm. Now, in a second it will be clear why it's infinity norm, but it's defined by maximum on all of the elements, absolute elements inside the vector A. So you're taking all of the absolute values in the A, which is A1 absolute value, A2 absolute value, and so on, until you get to absolute value of AN, and picking the highest one, the biggest one. And this is the value of that norm. Now, P norm is basically generalization of all of those three norms together. For different values of P, you'll get different norms. For example, if P equals to 2, which is here, you'll get Euclidean norm. For P equals 1, you will get Manhattan norm. For limit case where P goes to infinity, you will get maximum norm. And this is how it is defined. Instead of square root, we are using P's root of sigma of absolute values of all of the elements of vector AI when I goes from 1 to the last element n, but to the power of P. In other words, this is how it looks like. So pay attention, if P equals to 1, basically square root disappears here, and then you get A1 absolute value to the power of 1 plus A2 absolute value to the power of 1 and so on, which is exactly that thing. If you put P equals 2, you get that thing. If you get P limit goes to infinity, you will get to this one. Now we are ready and have enough terminology to discuss length, area and volume of simple shapes. Okay, now let's try to work with more dimensions and handle areas and volumes. But let's start with simple interval. We have interval with endpoints x1 and x2. For that interval, the length of that interval clearly will be defined x1 minus x2 or x2 minus x1, depends on the order of the points that we put it on that interval. So we need basically absolute value of that expression. Now, let's say you have triangle with points x1, y1, points x2, y2, and the third one is x3, y3. To compute that area of the triangle, given those 3 points coordinates, you need to compute something like that. This will be the area. Absolute value of that expression, which is 1/2 of x1, y2 minus x2, y1, and so on. So it's pretty complicated, and I'm not showing right now how to get to that formula, but this will be the area of just any general triangle with points P1, P2, and P3. Now, we go into third dimension. In third dimension, the equivalent of triangle will be tetrahedron, which looks like that. If you want volume of that simple shape, comparatively simple shape, you need to write 1/6 of x1, y2, z3 minus x1, y3, z2 minus x2, y1, z3 and 20 more terms until you get to the last one, x4 multiplied by y3 multiplied by z2. Now, this could be also positive or negative, so you need to take absolute value of that to find volume of tetrahedron here. Okay, let's summarize. So we have length here is absolute value of that thing. Area is that thing. Volume of tetrahedron is that thing. And you clearly cannot see any relation between those things yet. I will show you the proof of the triangle formula a little bit later, but you will need to remember that you have all kind of other complex things, and you need to believe me that this is how you actually compute the volume of general tetrahedron with 4 points. So this will be point x1, y1, z1. This point is x2, y2, z2, x3, y3, z3, and x4, y4, z4. And this is how you compute that volume. I want to remind you also that I started that lecture with saying that length, area, and volume are almost the same, or same in some meaning of the word same, or generated by the same principle. And from those formulas you cannot identify what are those principles. And this is why we will need to go to a little bit more definitions of things from linear algebra to see what is the relation between all of those three. Before we move on to next definitions, I want to show you how I prove the formula for area of a triangle that I showed you in the previous slide. Let's say you have some sort of triangle like that. And then you also have height of the triangle like that, which is getting on the base of the triangle. We will denote that thing by H and that thing by B. Also we need to denote the corner points. This corner will be point x1, y1. This corner will be x2, y2. And this corner will be x3, y3. Those 3 points are actually given on the triangle, and you want to compute the overall area of the triangle. From the school geometry you should know that area should be 1/2 h multiplied by b, which means height multiplied by the base. Also, from Pythagoras theorem you know that b could be computed as square root of x2 minus x1 squared plus y2 minus y1 squared. The computation of distance h is a little bit more tricky. You need to know a little bit of analytic geometry and the formula for distance between point, which is given, and straight line. So if you have some point, and then you have straight line, and the point has coordinates x, y, and straight line has, let's say, alpha x plus beta y minus 1 equals 0 equation, then the formula will be given the following way. The distance h will be given by absolute value of alpha multiplied by x plus beta multiplied by y minus 1, which is basically equation of line absolute value of it, divided by square root of alpha squared plus beta squared. Now, in our case, basically all of those alpha and beta coefficients we need to find first. The point is given to us because xy is actually x3 and y3. To find the h, we need to find what is that line. Straight line which is passing through x1, y1 and x2, y2. So what kind of line is that? This line should satisfy the following equations. Those equations will be alpha x1 plus beta x1 equals to 1, because this is the equation of line, and it should pass through the point x1, sorry, it should be y1. And similarly for the second point, x2 and y2, it's alpha x2 plus beta y2 should be equal to 1. So it's passing also through the second point. Now the solution of those two equations, we need to find what are the alpha and beta. To remind you how we solve system of quadratic equations, we write it as a matrices. So technically we write something multiplied by vector of unknowns that we want to find, which are alpha and beta, equals to vector of free coefficients, which is 1 and 1 in that case. So what are the coefficients of alpha and beta? First one is x1 in the first equation, second one is y1 in the first equation. Here you have x2 and y2. Remember that all of the x's and all of the y's are given because those are the parts of the definition of the triangle that we are talking about. So how you solve that? To solve it, you need to find alpha and beta vector, which is, let's call it matrix A. It's that matrix A inverse multiplied by 1, 1. Now what is that inverse? You should know the formula already from 2 by 2 order inverse. This is 1 over something which is called determinant of A, and determinant of A is basically x1 multiplied by y1 minus x2 y1. So this is just cross multiplication of this one by this one minus cross multiplication of this one by this one inside of the matrix, and then we're flipping y2 and x1 and then making negative sign here and negative sign here, and this is how you invert matrix 2 by 2 multiplied by 1, 1, which will be equal to the following vector. It will be y2 minus y1 divided by det A. Pay attention that here I'm using that just for shortcut of that notation. I will define determinants in the next slide, but here I will just use that as some given constant expression, determinant of A. And the second element will be x1 minus x2 divided by det A. So this will be alpha and this will be beta. Now let's put those numbers back into the formula of h here. So this is what we will get. First of all, alpha x will be y2 minus y1 divided by det of a multiplied by x plus beta is x1 minus x2 divided by determinant of a minus 1, and bottom part will be y2 minus y1 square plus x1 minus x2 squared, all of that divided by determinant a squared. Now pay attention that if I'm taking that thing out of the square root, I will get the following. It will be absolute value of determinant of a multiplying another determinant, and at the bottom I will have y2 minus y1 squared plus x1 minus x2 squared. And here I will have the same thing, y2 minus y1 divided by det a multiplied by x plus x1 minus x2 divided by det a minus 1 absolute value. Now pay attention to something interesting. That entire thing is essentially b. This is zb. This is the same formula. Now we can start computing actual area. I'm copying the same formula. It's 1/2 multiplied by b multiplied by h. But what I will get? I will have b multiplied by h. H is something divided by b. Here I will have det a, and here I will have all of those things which I had before. So we can cancel b, and we will get 1/2 multiplied by det a, determinant of a, and multiplied by y2 minus y1 divided by det a x. And pay attention what kind of x is that right now. Since we are talking about distance between point x3, y3 to that thing, this will be x3, and this will be, here I need to add here y3. So it's x3 plus x1 minus x2 divided by det a multiplied by y3 minus 1 absolute value. So this is how we get to the area. Now let's see what we get here. Determinant could be positive or it could be negative, determinant of a. Depends on the order of the numbers that we'll see it in the future. But let's say this one is negative. So it's smaller than 0, it's just a number. Because this is how we started that number. We had that thing, and this thing could be clearly positive or negative. So if this is negative, we can put it inside of the absolute value with negative sign. So it's 1/2 multiplied by absolute value of det a with minus multiplied by y2 minus y1 det a x3 minus again det a multiplied by x1 minus x2 divided by det a y3, and minus, which converts into plus det A. So those are cancelled, and this is what we get from here. It's 1/2 absolute value of y2 x3 with minus sign, because we have that minus here, plus y1 x3. This is from this one multiplied by this one with minus sign here. Now from the second part we get minus x1 y3 plus x2 y3, and from the last part we get plus determinant of A, and determinant of A is x1 y1 minus x2 y1. Now pay attention to that formula. This is exactly the formula for a triangle area that we found before, and this completes the proof. I have used already determinant in the previous slide just for convenience, but now I want to define it more formally. This will be also very helpful to discover something in common between area, length, and also volumes, and maybe we will be able also to describe it in more general terms. The second order determinant for the matrix A, which will be given like that, is defined like that. So this is how we denote it. We denote it with two vertical bars on the same elements of the matrix, and this is how it is computed. Pay attention that that second order determinant, as well as any other order determinant, will be just a scalar number. So it's just some manipulation on the values of the matrix values. So determinant of A1, B1, A2, B2 will be A1 multiplied by B2 minus A2 multiplied by B1. So you're taking A1, cross multiplying it by B2, minus A2 cross multiplied by B1. This is how it is defined. This is the determinant of the second order. Generally, the determinant of square matrix is denoted by two vertical bars like that, or det of A. All of the elements of A could be between those two vertical lines. And this is true not only for second order, just for any order. You can have multiple numbers inside. But the matrix has to be square. So the number of rows should be exactly equal to number of columns. Computation of higher order determinants could be done by reducing the order. And to reduce the order, we need to define matrix minor, which we will do in the next slide. A minor of the element Aij from the matrix ANN is a determinant that you get from the original matrix A after crossing out the row I and column J, which means you're just taking Ij, row I and column J, and crossing out row I and column J in the matrix, and the rest of the values you're putting in smaller matrix for which you're computing the determinant, and this is the minor of that specific element. For example, you have matrix A, which is 3 by 3. Let's say A11, A21, A31, and so on. And for example, you want to find a minor of A22. So this is the element that we are talking about. We are crossing out Z1 and Z row, and you're left with a few more values. So those are values which are left in the matrix. You compute in determinant of that thing. So it will be determinant of A11, A13, A31, A33. So those are the elements which left after you crossed out the row and column from this one. Or you can also write that the following way. It's A11, A13, A31, A33. Now, you know already how to compute determinant of second order, because this is given by the formula. It's A11 multiplied by A33, so it's cross multiplication here, minus cross multiplication here, so it's minus A31, A13. This is the minor of A22 from the matrix A. Let's take another example. Let's say you have 4 by 4 matrix like that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Those are the elements of the matrix, just numbers from 1 to 16. Now, you are interested in number 7 minor from that matrix. So pay attention, number 7 is here, which means this is element basically A to 3. You are looking for A to 3 minor of the matrix A. So you are crossing out that column and that row and writing all of the rest of the values that left. So you are looking for determinant of 1, 2, 4 because you're skipping 3, it was crossed out. Then you're skipping the second line because it's crossed out. And then 9, 10, 12, 13, 14, and skipping 15, 16. This is a determinant. Note that the order of minor is always by one matrix which is creating minor is always by one smaller than the original matrix. So if this matrix is 3 by 3, this will be 2 by 2. If this one is 4 by 4, this matrix will be 3 by 3. But pay attention that this will be scalar. So this will compute into a scalar number, which is just regular real number. Using minors of the matrix is very convenient to compute determinants of higher orders of that matrix. And we will see how to do that in the next slide. You can compute higher order determinants by developing them by any column or by any row. Both methods are completely equivalent and giving you the same solution and the same number. Now, let's start with the first one, developing by column, and then we will move to developing by row. Let's pick some column in the matrix A, and let's that column to be called J. Determinant of that general matrix A by n by n matrix A will be sigma from 1 to n on all of the rows, and I will be row and j will be column, of minus 1 to the power of I plus j multiplied by that element of the matrix Aij at the row I and column j multiplied by minor of the same element. So what it all means? Basically, let's start with the sigma and with that element. So what is minus 1 in the power to the power of I plus j? First of all, is if I plus j are even, which means number of rows plus number of the column is even number, then it will be just plus 1, which means nothing. So coefficient will be 1. If this number is odd, which means I plus j is odd number, then this number will be minus 1. So you can think about the entire matrix as a chessboard. It's just positive and negative signs. So it will look like that. So it will be always plus here, because it's I1 and J1, so it's 1 plus 1 will be 2, minus 1 to the power of 2 will be plus 1, and then location 1, 2 will be negative, because this will be 1 plus 2, and then again positive, negative, positive, negative, negative, positive, negative, positive, negative, positive, and so on. So it looks like a chessboard where plus means that you need to take coefficient Aij with positive sign, and if sign says minus, then you need to take it with negative sign. So it will be always A11 will be always with plus, and A12 will be always with minus, and A22 will always be with plus, and A32 will be always with minus, and so on. So all of the coefficients will have their own assigned sign. Now minor, you learned how to compute it in the previous section, and you can do similar things instead of by rows, by columns, you can do that by rows. So this will be completely equivalent thing. And the determinant of general matrix A will be sigma of almost the same thing, but instead of I will have J here because I'm developing by row now, not by column. So let's see some simple example. It will be more clear how you actually compute those things. Let's say you have to compute determinant of matrix, general matrix 3 by 3, and you will be developing that by the first row, for example. So it's A11, A21, A31, A12, A22, A32, A13, A23, and A33. You want to compute that determinant by the first row. You can pick any row or any column. So let's pick this one. I will show you later why it's convenient to pick one or another. So we're developing by that row. So all we need to do is to take the first element on that row, A11, with the appropriate sign, and A11, as I said, it's always coming with the sign plus because this is sitting here. So it's A11 multiplied by minor of A11. So what is a minor of A11? We're crossing out that line and that column, and we get A22, A23, because those are the elements who left, A32, and A33. So those are the elements here. Now we're taking the second component, A12, with the appropriate sign. So what is sign of that? Sign minus. A12, and those signs are always interchanging when you're doing that, so it's easy to remember. You don't need to look up here. Those signs will be always plus minus, or minus plus all the time. Now we're crossing out now this line, this column, and this line, and writing the rest of the coefficients: A21, A21, A23, A31, and A33, and plus the next coefficient, which is A13, multiplied, crossing out that column and that line, and getting basically to the coefficients A21, A22, A31, A32. And this is how you compute the determinant. Since all of those things already defined before with smaller order determinants, we can always write something like that. So it's A11 multiplied by A22 multiplied A33 minus A32, A23 minus A12 multiplied A21, A33 minus A31, A23 plus A13 multiplied by A21, A32 minus A31, A22. And this is the determinant of third order for that specific matrix that we have here, based on those computations, because this is what it is. I want to note here that it is easier to choose row or column with multiple zeros and to develop the determinant by that row and that column, where you have a lot of zeros. Why? Because most of those zeros will be just multiplying some other determinants, and they will disappear from the computation. So let's take some simple example. and we will see how we compute some matrix determinant of fourth order. So this is the determinant that I want to compute. It's 1, 2, 0, 1, 0, 1, 2, 0. And it's very convenient to compute it where you have multiple zeros here. So I want to compute what that determinant is. Pay attention that the most convenient line here is line 2, like row 2, because you have 2 zeros here in the row 2. And also it's convenient to develop it by the last column. Again, you have 2 zeros here in the last column. So let's develop by the last column. You can develop by the second row, it will get you to the same result exactly. So first of all, we're starting with that number. And we need to identify if the sign of that coefficient will be positive or negative. So let's start from here. Plus, minus, plus, minus. So it should be negative. So negative 1 multiplied by minor. In that case, the minor will be, of course, from the third order. So you're crossing out this one and this one, and you get 0, 1, 2, 2, 3, 1, 1, 3, 4. Now, we're moving to the second coefficient here. This is 0, so we can ignore it because we will be multiplying by 0 some determinant, it still will be 0, so it doesn't matter what determinant you have from there. Next one will be here. So will it be positive or negative? So since this one is negative, this one will be plus, and this one again will be negative. So it will be minus 5 multiplied, crossing out this one and this one now, and what is left here is 1, 2, 0, 0, 1, 2, 1, 3, 4. And the last one again will be 0, so it will be plus 0 multiplied by some determinant. It doesn't matter what is that. So totally we need to compute that thing. So it's minus 1 multiplied by determinant of that thing. Pay attention that this determinant is very easy to develop by the first row or first column. So let's do that. Technically, we can write minus 1 multiplied and developing by the first row, for example. So it will be that element first, which is minus 1, because this is second and not the first one, multiplied by determinant of the rest of the values, which is 2, 1, 1, 4, and then second value plus 2, and determinant of 2, 3, 1, 3. Now the second part will be of minus 5, so it's minus 5 multiplied, and here it's also convenient to develop by the first column or first row. So let's try to develop that, say, by first row again. So it's 1, positive 1, and then determinant of the values which are not here, which is 1, 2, 3, 4, and minus 2, which is here, minus all of the values which are not here, which is 0, 1, 2, 4. And this is what we need to compute. It will be equal 2 by 4 minus 1, minus 2, here 6 minus 3, minus 5, 4 minus 6, plus 10 multiplied by minus 2. Total it will be minus 9. So this is the value of the determinants that we are computing. We have a few very important properties of determinants. The first property is that determinant of A transpose equals to determinant of A itself. Let's see some simple example. Let's say you have matrix A, which is 1, 2, 3, 4. So 1, 2, 3, 4 determinant equals to the transposed version of the same thing, which is 1, 3, 2, 4. Let's see why is that, because this one is 1 by 4 minus 2 by 3, and it should be equal to 1 multiplied by 4 minus 2 multiplied by 3. This is exactly the same. For second order it's trivial, but for higher orders clearly you need more explanations to do, but it still will work for any order of matrix A. Second property is multiplication of one of the rows or one of the columns by a given constant multiplies the determinant by the same constant. Let's take a simple example. Let's say you want determinant of matrix 1, 2, 3, 4, but we will multiply that row by 2. So let's see what is the difference with the original thing. This will be determinant of 2, 4, 3, 4, which is 2 by 4 minus 3 by 4. It will be 8 minus 12, which is minus 4. Pay attention that the original one was 4 minus 6, which is minus 2. So minus 4 is basically twice the original determinant, which is minus 2. Another property is that when you change in two rows or columns, it changes the sign of the determinant. So if you're flipping that matrix upside down, for example, instead of 1, 2, 3, 4, you get 3, 4, 1, 2. That determinant will be equal 3 by 2 minus 1 by 4, and it will be clearly equal to 6 minus 4, which is positive 2 and not negative 2, compared to the original one, which is negative 2. Another property is adding or subtracting linear combination of rows, columns to other rows or columns is not changing determinant of A. Pay attention that rows are working only with adding some other rows, and columns are working only with adding some other columns. For example, if you add into some line some other line, or if you add into that line something which is proportional to another line, which is other line multiplied by some coefficient or some constant, it will not change the determinant. Let's see some simple example. Let's say we have matrix like that, 1, 2, 2, 8. Okay, and we want to compute determinant of that matrix. What we'll be doing for that? We will subtract twice the second line from the first line. So it's minus twice second row from first row. So this will be determinant, where the second line is still the same, 2 and h. Sorry, let's make it a little bit easier. So you'll want to reduce maybe first row twice the first row, from the second row. So you'll get determinant, where the first row is still the same, 1 and 2. From 2, we need to reduce twice the first row, which is twice 1, so it's 2 minus 2. And from 8, you'll subtract twice the first row, so it's 2 times 2. So you'll get determinant 1, 2, 0, 4, which we can easily compute as 1 multiplied by 4, and this will be 4. Pay attention that the original will be like that, 1, 2, 2, 8, and this determinant will be 1 times 8 minus 2 times 2. So let's compute it. It's 8 minus 4, and it's still 4, the same thing. There is one more important property of determinant, which is related to invertibility of specific matrix A. So we will start with following properties of invertible matrices A. So all of those properties should be equivalent, which means between any one of them you can put if and only if. So matrix A is invertible, which means that A to the power of -1 exists if and only if determinant of that matrix is not equal to 0. In other words, it means that if determinant of A is 0, the A will not be invertible. Another property to make matrix invertible or determinant not equal to 0 is AX equal to 0, which is basically a system of linear equations where all of the right parts, which are coefficients, equal to 0, has only trivial solution where x equals to 0. So this is called trivial solution of that system of equations. So you have some matrix A multiplied by some vector x to xn, and it will have only one solution, where all of that vector is vector of zeros. It's also equivalent to linear combination of rows is 0 only if all coefficients or weights are 0. So just to remind you what linear combination is, it's just alpha 1 multiplied by vector 1 plus alpha 2 multiplied by vector 2 plus and so on alpha n multiplied by vector n. Each vector is of course some sort of column vector like that of order n, so it's n by 1. This one is n by 1. So linear combination is that thing which is also a vector of order n by 1. Because sum of constants multiplied by vectors will be of the same size. So linear combination of vectors related somehow to determinant of A and related somehow to invertibility. Now the same thing happens with columns. So if you're taking linear combination of columns, it is 0 only if all coefficients are zeros. So this is how it looks like. So only if all of those coefficients are 0, then, and basically v1, v2, and vn are columns of matrix A, only then this matrix is not invertible if this equation is true only for all coefficients equal to 0. So this is what it means. The last two properties are called linear independence of rows or linear independence of columns. We will see more formally what linear independence is in the next slide. N vectors, and we will define those n vectors in space R to the power of m, which means every one of them has m coefficients from 1 to m, are linearly independent. So those vectors that we define are linearly independent if for all of the numbers alpha j, and those are just arbitrary random numbers or random coefficients, whatever you want, and those are just numbers, real numbers, that expression, which is linear combination of the vectors v1, v2, v3, and so on until you get to vn, so this linear combination equals to 0 if and only if all of those coefficients equal to 0. So this is the unique solution to that system of equations. So one direction here is obvious. So if all of the coefficients are 0, then this direction is trivial, because clearly 0 multiplied by some vector plus 0 multiplied by some other vector plus 0 multiplied by third vector and so on, it clearly will be 0. But that direction is not always obvious and sometimes not true, and sometimes is true. So let's take a few examples. Vectors 1, 2 and 2, 4 are not linearly independent. And this is because we can write them like that. It's 2 multiplied by the first one minus 1 multiplied by the second one equal vector of zeros. So clearly those coefficients are not 0, but their linear combination is 0. But you clearly can ask me, how should I know those numbers? Like, where I'm getting those numbers from? So to identify those numbers, I need to write system of equations. First of all, I'm writing them in general form, like that. And then, more explicitly, it's alpha 1 to alpha 1 plus twice alpha 2 for alpha 2 for alpha 2. And this should be equal to 0, 0. And I expect to see only trivial solution to alpha 1 and alpha 2 if this will be linearly independent vectors. So this is the system that I've got from this one. So it's alpha 1 plus twice alpha 2 equals 0, and twice alpha 1 plus 4 alpha 2 equals 0. So let's solve that system of equations. So alpha 1 equals minus twice alpha 2, and from here twice alpha 1 is minus 4 times alpha 2 plus 4 alpha 2 equals 0. So this is trivially true. So it's always true for any alpha 2. So technically I have infinite number of solutions to that system of equation, and I can pick any pair of numbers which will satisfy just that thing. So here I can pick alpha 1 equals, for example, 2, and alpha 2 equals minus 1, or any other pair which will satisfy that kind of equation. And those are exactly the numbers that are sitting here. So those are solving that system of equation. But I can take any other pair of numbers which will satisfy that equation, and I will get the same thing here. I will get 0 and 0 vector as the output. So those vectors are not linearly independent. Let's take another example. We will take vector 1, 2 and vector, say, 5, 6. Those vectors are linearly independent. So, how do I know it? Let's write it in general form. I have alpha 1, 1, 2 plus alpha 2, 5, 6. And this is equal to alpha 1 plus 5 alpha 6 alpha 2 twice alpha 1 plus 6 alpha 2 equals 0, 0. So this is the system of equations that I'm solving here. It's 1, 5, 2, 6 multiplied by alpha 1, alpha 2 equals 0, 0. Now, this matrix is clearly invertible, so you have only one possible solution, that alpha 1 equals alpha 2 equals 0. So how should I know that this matrix is invertible? I can just compute the determinant of that matrix. So it will be 1 over determinant, which is 1 multiplied by 6, plus minus 2 multiplied by 5, and multiplied by matrix, which is inverse of that matrix. 6, 1, minus 5, minus 2, and multiplied by 0, 0 will give you alpha 1, alpha 2. So since this determinant is not 0, you don't have division of 0 by 0 here. So the only solution will be just some matrix multiplied by some number multiplied by vector of zeros. But matrix multiplied by vector of zeros is always 0. And this is why I know that this is the only possible solution for alpha 1 and alpha 2, and then those two vectors are independent. Historically, the first use of determinants was for solving system of equations, and this is how they were defined. In 1750, Swiss mathematician Gabriel Cramer proposed general formulas for solving any system of linear equations. Only 100 years later, determinants actually invaded all of the other math areas. So let's see how he proposed to solve general system of equations. Let's have some general system AX equals to B. This is linear system of equations, and A is matrix, X is vector, and B is also vector. So it will look like that. It's some matrix multiplied by some vector of x1, x2 to xn, and this matrix is n by n. So it's n system of n equations with n variables, and it equals also to n constants b1 to bn. This is a system of equations that we want to solve. And you know that this is also equivalent to a11 multiplied by x1 plus a12 multiplied by x2 plus and so on equals to b1. And then you have n equations of that kind, and then you have an1 x1 plus an2 x2 plus and so on equals bn. So all of those representations are completely equivalent. So you want to solve generally the system of equations if you have the matrices A and you have vector B. So we want to find X. So we already saw that we can solve it just by multiplying A inverse by B and then to compute X. But actually how you compute that A inverse sometimes might be complicated, especially for big systems of equations. So this is what Gabriel Cramer proposed to do. This is a solution. So element xi of the vector x will be equal to determinant of aj, and I will define aj in a second, divided by determinant of the matrix A. That's it. This is the formula. So this formula will help you to identify all of the elements xi, which is x1, x2, x3, and so on, to identify all of the roots of that system of equations. Now, aj is the matrix A with some modification. So in matrix A, where the column J is replaced with B. Which means we are taking just regular matrix A, replacing column J in that matrix with vector B. Each time it will be different column because J will be moving from left to right, from 1 to n. And then we're computing X with the same thing. So this is xj actually. So J will move from 1 to n. Before I show you example how to do that and how to work with that formula and how to compute solution of system of equations in general, I need to give you a few notes. Those are very important notes to understand how that system works. So, note number 1, if determinant of A equals to 0, not equals to 0, this means that you actually can divide by that thing, and this will not be infinity or anything like that. Then we will have single solution. If the determinant A equal to 0 and for all j the determinant of aj is not equal to 0, which means you have something which is not 0 divided by something which is 0, there is no solution. And third one, if determinant of A equals to 0 and there exists such a J for which determinant AJ equals to 0, which means it's division of 0 by 0, then we have infinite number of solutions. Okay, now we can move to the example of how actually to solve system of equations using that formula. Let's solve the following system of equations. Let's say we have two equations of that kind. 2x plus 3y equals 8. And then 7x minus 5y equals minus 3. From here, matrix A will be the matrix of coefficients 2, 3, 7, minus 5. B will be vector 8 minus 3. So x will be the first one, it's like x1 will be one determinant divided by another determinant. On the bottom part we always have the determinant of A. So just to remind you, this is det of AJ. In that case it will be j equals 1. And this is det of A. So this is determinant of A, 2, 3, 7, minus 5. And here is the same thing, but the first column we're replacing with B. So that column we're replacing with vector B, which is 8 minus 3. And then repeating the matrix A part, which is 3 minus 5. Now, for computation of y, we are doing the same thing. Here is still the determinant of 2, 3, 7, minus 5. And here we're replacing the second column with 8 minus 3 from the B. And here we're copying the A matrix. Now we can compute both of those things. So first one will be minus 31 divided by minus 31, which is 1. The second one will be minus 62 divided by minus 31. And this one will be 2. So basically x equals 1, y equals 2. Those are the solutions of that system of equations. Okay, now we can get back to our question of the relation between length, area and volume. Let's start with the interval laying on the real axis with endpoints x1 and x2. So you'll have point 1, point 2, point 1 will be x1, point 2 will be x2, or you can switch the direction and then it will be p2 and p1, but it doesn't matter in that case. The length is written as x1 minus x2 absolute value, which could be also absolute value between x2 minus x1. So this is the length. This length we obviously could also write as the following determinant. So this determinant will be x1 minus x2 equals 1 over 1 multiplied by determinant of x1, 1, x2, 1, which is exactly cross multiplication of x1 by 1 minus x2 by 1. It will give you exactly the same thing, which is x1 minus x2, which you will denote by p1, p2, for simplicity of the notation. So this is basically distance between points p1 and p2. So that determinant of that kind, which is x1, 1, x2, 1, will be denoted like that. You just need to remember that notation now because it will become clear a little bit later why I'm using that kind of notation. Similarly, the area of a triangle on a plane xy with vertices p1, p2 and p3. Let's select those. So p1 equals to x1, y1, p2 equals x2, y2, and p3 equals x3, y3. So this area equals to the following determinant: 1 over 1 multiplied by 2, and determinant of x1, y1, y, x2, y2, 1, x3, y3, 1. And I will denote it by p1, p2, p3. So you have 3 points, p1, p2, p3. That determinant, I will say that this is p1, p2, p3. Now, if you open and develop that determinant by any row or by any column, this is exactly what you will get. This is area of a triangle. Finally, we can talk about the volume of tetrahedron. So, for tetrahedron with vertices p1, p2, p3, and p4, where basically pi point is something like x, I, y, I, and z, I. So it's three-dimensional coordinates right now. You probably can already guess what I will be writing in terms of determinant based on the previous ones, but I will write it anyway. So I will call it p1, p2, p3, p4, and this determinant will be 1 over 1 multiplied by 2 multiplied by 3, and determinant that you might guess from the previous ones by extrapolation: x1, y1, z1, 1, x2, y2, z2, 1, and so on. This is exactly what this formula is. This is volume of that kind of tetrahedron with general 4 points defined in any three-dimensional space, points from P1 to P4. Okay, let's summarize. The length of the interval P1 and P2 is that kind of determinant. The area of triangle with general given points P1, P2, P3, this is that kind of determinant. The volume of tetrahedron with general points from P1 to P4 is that kind of determinant. Generally speaking, length, area, and volume equal to the absolute value of those quantities. Do you see the pattern here? Just stop for a second and look on those three determinants and try to recognize the pattern. Note that constant outside of the determinant is 1 over n factorial, which is 1 divided by 1, multiplied by 2, multiplied by 3, multiplied by 4, and so on until you get to n. This is 1 over n factorial. Now, can you propose a generalization of length, area, and volume for a higher dimensional space, like 4-dimensional space or 5-dimensional space? How about hypervolume in 4D with coordinates pi, which are x, y, z, and w is index I? Can you do that? If you can, then you can easily understand why I started that lecture with saying that volume, area, and length have a lot in common, or they are coming from the same principle. Clearly, the determinants from the previous slide might be positive or negative, depends on order of points we choose. because I want to remind you that changing two lines in determinant is changing its sign. So we need to agree on the order of points, and for that we will use arbitrary but standard axis directions. For example, single axis, which is one-dimensional, will be in that direction. When you have plane, you'll have x and y in those directions. When you'll have three dimensions, this will be the direction. It will be x, y, and z. It's very important that we will always use the same direction for all of the coordinates. Otherwise, the determinants and their signs will not work. So we'll always use that standard representation of coordinates. Now, when we agreed on the direction of the axis, why do we need to put points in the determinant in the counterclockwise direction to get a positive result of the area? Let's try to understand it, how it works. We can start with the simplest case. Let's say we have the following triangle, which is very simple. So this is how we agreed to call that, x and y. And now the triangle will be like that. This will be 1, and this will be also 1. And we will have counterclockwise direction of the points. So the first point we can choose here, for example, P1, this will be P2, and this point will be P3. So those are the 3 points that we have, which are defining the triangle. In that simplest case, we can write that P1 equals 1, 0, P2 equals 0, 1, and P3 equals 0, 0 coordinates, and the area, which is defined by the determinant, is 1/2, 1, 0, 1, so it's P1 point with 1 at the end, P2, 1, and P3, 1. And this determinant, when we will develop it, for example, by the first column, it's 1 multiplied by 1, 1, 0, 1. So it will be 1 multiplied by 1, which is 1 positive. Now please try to follow the argument. By continuous deformation of the triangle that we have here, we can move the points P1, P2, and P3 to any other set of points with the same counterclockwise direction, without letting them to become collinear. So every one of those points will move by some trajectory and will move to some other point, P1 tilde, and this point will move also somehow to some other point, P2 tilde, and this point can move to any other point, P3 tilde. Now, if we preserve the same counterclockwise direction of the triangle, they will not become collinear. And collinear means that they all sit on the same straight line. So those are collinear points where they are sitting on the same line. When we move the points continuously, our determinant also will change continuously. It is obvious that the determinant could become 0 only when all 3 points are collinear, because this is the only case where the area represented by the determinant is 0. So the determinant will technically preserve the area all the time, the sign of the area all the time. In other words, this means that the determinant will keep its positive sign, because to change continuously from positive value to negative value, it has to pass through 0. And this is impossible because we prohibited collinear points. In conclusion, counterclockwise direction of points will give you a positive triangle area all the time, no matter what kind of triangle you choose. Now I want to show you why using both positive and negative signs might be useful in computations of areas. Let's get back to our triangle P1, P2, and P3. Let's say this is some general triangle. And we'll select points P1, P2, and P3 to describe the triangle. Every vertex will have, of course, x and y coordinates, so each one of those P1, P2, and P3 are vectors of size 2 by 1. Now, let's also connect all of those vertices into the point P0, which will sit somewhere inside of the triangle. So we'll connect that point here, here, and there by straight lines, and we'll call that point P0. Now, from one triangle we actually created three smaller triangles, but the area of overall triangle P1, P2, P3 is the sum of areas of those smaller triangles with an inside point P0. Now, how can we compute it if we define the same direction, which is counterclockwise, in every one of those triangles? So here is where my definition of those determinants for computing area of a triangle comes handy. The area of the original triangle could be written as a sum of areas of three triangles like that. So it's absolute value of P1, P2, P3. This is the area of overall triangle, equals the area of triangle P0, P2, P3, which is starting from that point and going that way, plus the second triangle, which is P0, P3, P1. So this is the second determinant, and absolute value of that determinant for that triangle. And the third one, plus absolute value of P0, P1, and P2, which is that triangle. Since we are using always counterclockwise direction from our previous discussion, all of those determinants are positive. Therefore, we could remove all of the absolute values, so we can write the following. So P1, P2, P3 determinant equals the area of P0, P2, P3 plus P0, P3, P1 plus P0, P1, P2. Now I claim that that formula is true even if P0 is outside of the triangle. So let's see what I mean by that. Let's see what we have if P0 is outside of the triangle. Let's say we have the same triangle, something like that, and then the point P0 is somewhere here. Now let's connect all of the points. This will be still P3, P1, P2, and now I'm connecting all of those points to P0. So the area of the original triangle, which is here, and this is what we have here, P1, P2, P3, is computed in that direction, which is counterclockwise. Now the second one is P0, P2, P3. So it's P0, P2, and P3. So this is the area of the triangle. It's still going the same way, because it goes from this one to this one to this one, counterclockwise. So it's still positive, and we're adding to the green area that brown area. Now the third one is P0, P3, P1. So it's P0, P3, and P1, which is that triangle. Now we're still going in the positive direction here, and positive direction here, and positive direction here. which means this is also positive area. We are using that with plus. So we added to the green area, we added brown area, we added red area, and now we have the last one. We have P0, P1, and P2. So this is the area. Pay attention that now we are going against the all previous directions, which is clockwise, which means that this thing should be negative. And if I subtract from the green area with added brown area and red area the cyan area, this will be exactly the area of the original triangle, which means if I'm adding brown one, again, I don't need to add green one first. So if I add that triangle plus that triangle and subtracting that triangle, the area will be of the original triangle, which is here. And this is exactly what I wanted to prove. Okay, now I have that great formula for computing triangle area based on 3 other triangles, which is triangulation of the triangle. And let's write that formula again. So this formula is P1, P2, P3 equals P0, P2, P3 plus P0, P3, P1 and plus P0, P1, P2. Now I want to prove that formula formally using some interesting determinant. So let's develop the following determinant: x0, y0, 1, 1, x1, y1, 1, 1, x2, y2, 1, 1, and x3, y3, 1, 1. Pay attention that 2 lines in that determinant are the same, which means that this determinant equals to 0. It's always so. If you have matrix with 2 columns or 2 rows which are the same, the determinant of that matrix will be always 0, and this matrix will not be invertible because you have linearly dependent columns. Clearly the last column dependent on the previous column, they even equal, so they clearly linearly dependent. Now we know that that determinant is 0. If you don't see it right away, you can actually compute it and see that this determinant is 0. Now let's develop that determinant by the last column. Okay, it will be the following. It will be minus 1 multiplied by determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1, because this is what gets us here, plus 1 multiplied by x0, y0, 1, x2, y2, 1, x3, y3, 1, minus x0, y0, 1, x1, y1, 1, x3, y3, 1, and plus the last one, x0, y0, 1, x1, y1, and x2, y2. Now let's see what it means. So this one is basically minus 0.1 with coordinates x1, y1, 0.2 with coordinates x2, y2, and 0.3 with coordinates x3 and y3. Okay? Multiplied by 2. Because this is determinant without 1/2 before the determinant. Okay? Plus twice. Second one is P0, P2, and P3. Minus 2. This one is P0, P1, and P3. And the last one is P0, P1, and P2. Clearly 2 could be cancelled everywhere. this could be moved to that side, which is all of that is equal to 0, so it could be moved to the other side, and you'll get P1, P2, P3 equals P0, P2, P3 minus P0, P1, P3 plus P0, P1, P2. But pay attention that this one is the same one as P0, P3, P1, because this is just changing of two lines in the determinant, and then it's changing the sign of the determinant, so it's plus that thing. And now compared to our original formula, this is exactly the same thing, so this concludes our proof. Now, why all of that is useful for anything? Because we can use that triangulation rule and that formula, which works always for any location of point P0, for finding areas of polygons, which is just general multi-vertex shape we want, and it could be anything in space. Let's draw something pretty random like that. Okay, now let's select the points P1, P2, P3, P4, P5, and so on. How we can compute area of that kind of polygon, which is given by just coordinates of the points from P1 to P8? We will select some point in the middle somewhere, which we'll call P0, and we will connect that point to each one of those points. So this point will be P0 inside. Clearly each one of them will be having coordinates x and y. But now, if we define the same direction of movement in every one of those triangles which were created by that, we can just add all of those areas as we have done before for a triangle. So this is what it will be. You'll have P1, P2, P3, P4, and so on to Pn area equal to P0, P1, P2 plus P0, P2, P3 plus P0, P3, P4 plus and so on until you get to P0, Pn minus 1, Pn, and then the last one is P0, Pn, and returning back to P1. It will work every time for every number of vertices you want. So this formula is true for any polygon, and it will give you the right area for any given polygon with any given coordinates. How about computing the area of any closed curve? Let's choose the origin point inside of that shape that we want. Let's say you have some sort of curve, and then you're selecting some middle point as origin. For simplicity, we can select that P0 to be just 0, 0. So if this is not exactly 0, 0, we can move that shape to include that origin, and this still will have the same area, of course. By now you should also know that it doesn't matter where you choose that point, so it will not affect the computation itself. But for graphical simplicity, we will choose it inside. Okay, so let's pick one specific point on that curve which we'll call Pi. So that point clearly will be having coordinates xi and yi. We want to divide the entire shape into tiny triangles, which are infinitesimal triangles. Okay? And then the overall area of the closed curve will be sum of those tiny triangles. So the triangles should be small enough that the approximation of that line will be almost linear. So those 2 points, this point and this point, which is pi plus delta pi, should be very close. Okay, so now let's put some definitions. We will say that pi is xi, yi, and delta pi is basically some dxi, which is infinitesimal addition to the xi and infinitesimal addition to the yi. So z delta pi will be defined like that. Now let's try to compute the area of that tiny infinitesimal triangle here. It will be like that. Using our formula, it will be 1/2 and then determinant from the point 0, 0, which is p0, 1, then xy, 1, and then x plus dx, and y plus dy, 1, which will give us the following solution. It's 1/2 multiplied by x dy minus y dx. Now, when we're adding along the line all of those triangles together, the limit of that sum will be, of course, integral. It will be the following integral. So area is 1/2, which is constant, which is coming out of the integral, multiplied by integral of that expression that we have, x dy minus y dx. And this is essentially the area formula for any closed curve.